Hey guys, so a classmate asked, what is optical isomerism in chemistry? To understand optical isomerism, we first have to understand what isomers are. Isomers are molecules that have the same molecular formula, but have a different arrangement of the atoms in space, which does not include changes in arrangement due to the molecule rotating as a whole or rotating about particular bonds. Stereo-isomers are a form of isomers that have different spatial arrangements of the atoms, but have the same connectivity between them, which just means it contains the same number of and kinds of atoms/bonds. Optical isomerism is one form of stereo-isomerism, with simple substances that show optical isomerism existing as two isomers known as enantiomers. Optical isomers are named as such due to their effect on plane polarized light. To understand what plane polarized light is, let's understand the following thought experiment. Imagine tying a piece of thick string to a hook in a wall and then shaking the string vigorously. The string will be vibrating in all possible directions, giving it a complex overall motion up and down, side to side, and all the directions in between. Now suppose you pass the string through a vertical slit. The string is a snug fit in the slit, and therefore the only vibrations still happening on the other side of the slit will be vertical ones. All the others will have been prevented by the slit. What emerges from the slit could be described as plane polarized string, because the vibrations are only in a single vertical plane. Now look at the possibility of putting a second slit on the string. It is aligned at 90 degrees to the first one. The string will stop vibrating entirely to the right of the second slit. The second slit will only let through horizontal vibrations, but since there aren't any after passing through the first slit, no vibrations will be apparent. Light is also made up of vibrations, electromagnetic ones. So some materials can screen out all the vibrations apart from those in one plane, and they can produce plane polarized light. An optically active substance is one that can rotate the plane of polarized light. If you shine a beam of polarized monochromatic light of only a single frequency or a single color, through a solution of an optically active substance, when the light emerges, its plane of polarization is found to have rotated either clockwise or anti-clockwise. Chemists use polarimeters to characterize optical isomers by measuring the angle of rotation of the plane of polarized light. A solution of one enantiomer that rotates the plane of polarization in a clockwise direction is known as the plus form. For example, one of the optical isomers or enantiomers of the amino acid alanine is known as plus alanine. A solution of the other enantiomer that rotates the plane of polarization in an anti-clockwise direction is known as the negative form. So the other enantiomer of alanine is known as negative alanine. We need to note that we cannot use optical rotation to establish the absolute configuration of an enantiomer, because the sign of optical rotation for a particular enantiomer may change when the temperature changes. To name the enantiomers of a compound unambiguously, their names must include the handedness of the molecule through the use of RS nomenclature. However, if the solutions are equally concentrated, the amount of rotation caused by the two isomers is the same, but in opposite directions. When optically active substances are made in the lab, they often occur at a 50-50 mixture of the two enantiomers. This is known as a race mix mixture or race meet. It has no effect on the plane polarized light. Optical isomers are often described as being non-superimposable mirror images of each other, which means the molecules cannot be placed on top of one another to produce the same molecule. A way to visualize this is to think of our hands. Our left hand is a mirror image of our right, yet there's no way our left thumb can be over our right thumb if our palms are facing the same way and placed over one another. Optical isomers also have no axis of symmetry, which means that no line can bisect the compound such that the left half is a mirror image of the right half. A molecule that has no plane of symmetry is described as chiral. In the following molecule, the carbon atom, represented as a black circle, has 4 different groups attached to it, which leads to a lack of symmetry in the molecule and is why we describe the carbon as a chiral center or an asymmetric carbon atom. The molecule on the left does have a plane of symmetry, and therefore is described as being achiral. However, only chiral molecules have optical isomers. Since structure and shape often determine how a molecule interacts with other molecules, optical isomerism and its properties are especially important when it comes to developing and manufacturing drugs and pharmaceuticals. Many of the receptors within our body that respond to drugs are chiral, and therefore the chirality of the drug is incredibly important. A simple example of this is with the molecule carbone. Both isomers, so-called S and R carbone, bind to receptors in our nose, which means that we can smell them. The two optical isomers smell quite different to one another, however. R-carbone is the main component in spearmint oil and smells like mint, whereas S-carbone is found in caraway seeds. I hope this video helped you to learn more about optical isomerism.